Okay, hello. I'm Monica Beckwith. I am a Java JVM garbage collection performance engineer. Today I'm going to talk about contention, monolithic locking, and the improvements in Java 9. I work for myself. It's called Code Caramel LLC. A little bit more about me. I started with advanced micro devices. I was a performance engineer for the compiler team. They had this new release called Opteron, 64-bit processor, so we were trying to get optimized compiler instructions. And then I moved to JVM performance engineering right when I was at AMD, and that's how I got hooked onto Hotspot. And since then, I've worked for Sun, Oracle, and then for myself now. And I primarily work with Hotspot JVM, which is also the OpenJDK JVM. And so they're both similar, Oracle Hotspot and OpenJDK Hotspot. And one of the things about Java 9 is that, well, you hear so much about modularity, right? But there's so many more improvements, especially performance improvements in Java 9, and one of them is contended locking. There are others like string density is a big improvement also, but that's for some other day. Okay, and so the last title that I had at Oracle was Garbage First Garbage Collector Performance Lead, and I'm going to talk about Garbage First, which is going to be a default garbage collector for Java 9. So I'm going to talk about that tomorrow at noon, I think. So let's talk more about the agenda. So what I want to do, I want to give a background on what is monolithic locking. Okay, how is that important, you know? And then what are the improvements up until Java 9, okay? And then we'll build a problem statement. My background is performance engineering, so I would like to first explain what are the improvements, and then I'll walk you through a performance engineering process. And then we'll try to solve, as if this was a problem given to us as a performance engineer, trying to solve and see how we can measure improvement in performance for contended locking, okay? And the way I will do it, I'll demo a tool that I like to use. I've been using it for more than 10 years now, called Developer Studio. So now it's called Oracle Developer Studio. And I used it first for C compiler, and now I use it for Java. I've been using it for Java, like I said, for more than a decade. The way we're going to do it is, because this improvement is in Java 9, we're going to compare it to Java 8 and see how the improvement shows itself, right? And then summarize the observations. So let's set the stage. So what are locks, right? We have a single thread T trying to execute a synchronized method. We have a synchronized method basically, and a single thread T comes along, it's trying to execute that. So by itself, this is known as uncontended lock, because there's a single thread that's trying to access the synchronized method, right? And what is uncontended lock? It's basically also known as deflated lock or lightweight locks. If you're used to OS terminology, they're lightweight locks within the operating system. So in its simplest form, in the JVM, you have something called compare and swap that you can use to store the pointer to the lock in the object header. So every Java object has a header and a body. Within the header, you have the mark word and other things. And in that mark word, you can have information about the lock itself. So a lightweight lock is as simple as doing a compare and swap instruction, okay? Now, what if a different thread U wants to come along and it wants access to the synchronized method? So now we have contention. Previously, we had a single thread, but now a different thread wants to come along and acquire the same lock. So that's called contended lock. And contended locks are known also as inflated locks or heavyweight locks. Up until Java 9, well, the code is still there, but up until Java 9, these used to take slower path, which means that once you know there's inflation, you cannot do certain optimization that would designed for uncontended locks. So they go through the slower path, and these are expensive. So with Java 9, the optimization is to take a quick enter based on certain tests, and then don't go to the slow path if you can do every work in the quick enter, okay? And we'll talk more about that. With Contended Locks, we have to know that we have to keep information on all the contentions, all the threads. So there's something called wait sets. So every object has a monitor, and every object monitor has a wait set. So who is waiting on acquiring that object's lock? Those threads will go and wait in the wait queue. Okay? That's what wait sets are for. So if I had to draw something like that, that's the object monitor. You have the monitor enter and monitor exit. And then you have the wait queue where your wait sets are maintained. Okay? So the way the communication happens is there's the wait signal. So if I'm already, if the monitor is already acquired by some thread, then it'll give notification saying, please wait to the other threads, please wait. So they go and sit in the wait queue. When the current thread is done with its object monitor work, it'll go and say notify, which means go ahead and release it. And then the next thread can acquire the lock. So that's how it looks when it's contended. So let's go get a little background on the improvements that were in the JDK so far. So the first improvement is also called bias locking, and it's for uncontended locks. So remember when I said that when you are uncontended, then all you have to do is compare and swap instruction. But with bias locking, the assumption is that the thread that acquires the lock will always be the one using it and reacquiring it. So why not bias that lock to the thread? So that means you don't really have to do the compare and swap every time, because you're the thread that has the lock and you'll keep the lock is what is assumed. So you're biasing the lock to the thread. So you only do compare and swap the first time, and then there's no more need of compare and swap instruction. The second one is lock elision, and it came as a benefit with respect to escape analysis. So escape analysis is a JVM runtime optimization in the Java virtual machine. And most of the JVMs out there have escape analysis in it already. And one of the benefits, and I'll show you a flowchart of how that happens, is that if the allocation does not escape the thread, then you don't need lock for that. You can elite the lock. Lock coarsening is when you have a bunch of synchronized statements, but if it's for the same object or towards the same, if the same thread needs to acquire that, why not just coarsen the lock so that you only obtain it the first time, and then you don't need it for the next few synchronized. So you don't need even cast if it was uncontended. So lock coarsening works for contended and uncontended, but it just basically reduces the lock to just a single time, the first time. And of course the contended lock, which was Java 9, which is introduced in Java 9. So we'll talk about that. And if you had a one-liner, it would be called the quick path. So now instead of the slow path, there's something also called the quick path, which based on certain tests, it can take, and you don't have to go down the slow path. So I was talking about escape analysis and lock elision, and this is what it is. So the way escape analysis work, if you have an allocated object that doesn't escape the compiled method, and the allocated object is not passed as a parameter to something else, then you can remove the allocation and the lock, right? And you keep the field value in registers. So you don't need to have that allocation. The allocation overhead is gone. It's directly into the registers. There's another way. Say your object doesn't escape the method, right? But it is passed as a parameter, so it may escape over there. Even then, what we can do, you can perform lock elision, and you use optimized compare instructions. So escape analysis is pretty ever since Java 7, it's pretty well tested, and it's a great addition to OpenJDK hotspot. And also lock collision comes as a benefit due to escape analysis. Okay? So now we have a background on what locking means and what inflated lock means. Let's try to build a problem statement, okay? So the way I want to build it is, because this is already there, Java 9 has it. So if you try Java 9 today, you will get this performance improvement. So I went to the JDK enhancement proposal page, and there it mentioned, the statement was, the summary was, improve the performance of contended Java object monitors. So contended being the key here. So we're looking for contention. Okay, so that's our problem statement. We're looking to have something that has a lot of contention, and we want to see if it has improved in Java 9. Okay. So then we'd go down the JEP page, and then these are the speed up targets. So they mentioned that they have quick path for monitor enter, monitor exit, notify, and unpark. So most of this I mentioned in the drawing, right? We said monitor enter, and it goes into a queue, and then you have notify and notify all. What we didn't say unpark is basically the thread. So it's time for the thread to come back when you're saying, hey, it's your time to get into the monitor queue and acquire the lock. So that's when it goes into unpark. Okay. So we'll probably see park instructions when we do look at the profile. So let's look deeper into what monitor enter entails. So during runtime, when you have a contended or inflated lock, usually before Java 9, like I said, it would go into object monitor and then take a slower path, as you can see. If I'm blocking it, I'm sorry. So as you can see here, right? With Java 9, what you see is the quick enter. So if you can do things in quick enter, then you don't have to go to slow enter at all. And things, so I was explaining this earlier to somebody. So things like notify. Remember we had a wait queue? If we know that these are the next threads that need to access or monitor, why not transfer them into the monitor enter queue? So usually that would have happened in slow enter, and that would take it extra cycles. But now we know we're inflated. Why not do it during quick enter while you're doing other things? So while the wait is happening and while the monitor enter and exit operations are happening, we could have moved the threads already. And that's simple optimizations as that are what make up quick enter subroutine. Okay. So this is the previously what I showed you, that was the optimization itself. Now, if we had to do, somebody came to us and said, you're performance engineers, I want you to show me that this optimization is in place, A, and B, that we actually see some improvement, right? So what approach as a performance engineer would you apply, okay? So there are two approaches that actually most engineers would go by. One is called the top-down, and the other is bottom-up. So the point of top-down is that I have the power. I have the power to modify code. Basically, it's my application. I have written this application. I know everything about the application, and I can do optimizations such that I can modify the code, right? And I'll tell you why this is necessary when we go talk about the bottom-up. So an application stack, and when we're doing top-down approach, this entire thing below the application and application ecosystem layer constitutes of the platform. Okay, so for me as an application performance engineer, all I care about is my application, and then everything else is what I'm supporting. What is my application supporting? So what OSs, different OSs, or cloud infrastructure, or different Java virtual machines, and all those things. So for me, what matters is my application. So any test that I'm doing gives me most information for my application, and the platforms are basically anything that my application supports. Okay. So when do we choose the top-down approach? when we're trying to improve our application. So we made changes to the application, and we hope that there's an improvement, and then we want to verify that in fact there's an improvement, okay? What about the bottom-up approach? In the bottom-up approach, I need the power. So previously I had the power to modify the code, but now I need the power to stress the platform. So what is important to me now, it changes. So the view changes. For me now, as a bottom-up performance approach, performance engineer, for me, it's important that I can stress my platform. I made changes to somewhere in the platform layer, and I want to stress it. And that's most important to me. So bottom-up approach for the same stack is basically your platform. Anywhere in the platform, if you have made some changes, you should be able to stress it. And the stress applicator would definitely be your application layer. But at that time, you don't care so much about the application and changes to the application, but what you care about is it being able to stress your platform, okay? So when do you apply the bottom-up approach? Like I said, when you want to improve your platform. So anything in the platform, so your Java virtual machine, your Java runtime environment, your operating system, your hardware, or anything in the platform layer then you would apply bottom-up approach. So we know the approach, but what's the process, right? The process is the same even if you're doing bottom-up or top-down approach. Step one is monitor. So when I say monitor, it means you could do active monitoring, which means you have a set of alerts based on all the requirements, your throughput requirements or your latency requirements or other requirements. If you have a loop, you want to make sure that the response time is within your bounds. So all those will become your alerts, and that becomes active monitoring. Passive monitoring is you sitting there and you're snooping. So network taps are passive monitoring. The third thing that I do most often than not is look at logs. So offline monitoring is what I call it. And I get a bunch of logs and I try to correlate timestamps and other things. I try to identify patterns. I try to parse the logs and plot them. So that's another way of monitoring. Now you have done monitoring, you have basically the ability to get information regarding when your thresholds or your system level agreements are crossed. Then the next step is profiling. So what does profiling help us with? Profiling gives us a visual into what's actually happening on my platform. So it doesn't matter if I was doing top-down or bottom-up. The thing is, my application is running on my platform, and profiling will give me a visual into it. You could do memory profiling, you could do code profiling, you could do OS level profiling, depending on what level of the platform you're interested in. But profiling is really important. We did profiling. The next is analysis, of course, right? We have all this information, so what is left to do is analyze the information. And analysis comes with, you can get basic analysis from tools, depending on what you're trying to analyze. There are very sophisticated tools out there that can help you analyze stuff. But eventually, putting all that information together and identifying and putting the patterns together, that's a performance engineer's job. So yes, you can use, everywhere you can use tools. Profiling, of course, tools. And some of the tools actually combine profiling and analysis together. So that's even better. But eventually, it's your job to look at the stack and say, okay, this is where I want to dive in deeper. And this is where I want to make changes. So that's when tune and application comes in. So you have the analysis, and you spend some time looking at the profile and analysis information, and then you think, I can tune it right here, and this is how I can go back to my benchmark or my application and redo this process till I meet or exceed my system level agreements, which are your SLAs. Sometimes people talk about quality of service, which is a step above SLA. So based on your quality of service is how you define your SLAs. So eventually the terms kind of correlate, but SLAs are more of something which is more of performance engineering focused. So quality of service may be more than performance engineering. So, so choosing the right approach. So what are we trying to do? If we're trying to improve the JVM, right? So going back to contended locking, right? What is the contended locking improvement? It's in the JVM. It's a JVM lock, right? Contended locking in the JVM. We're trying to improve it. So the improvement is in the JVM, which becomes the platform. So since we're improving the platform, we choose the bottom-up approach, okay? And my example will build on that. So the next topic is building our arsenal. So where do we start? I said all these fancy things about bottom-up approach, and we have the power, we need the power, but where do we start, right? So remember, when we talk about bottom-up approach, it's about stressing the platform. So we first need to know what we are stressing. Then, once you find out what we are stressing, we need to build either a benchmark or get a benchmark. If you're not an expert in that field, it's okay. I'm not an expert in many fields, you know, and so what I do is I look at industry experts and I try to get knowledge from them and find the right benchmark, basically. And then tools, right? Because we're going to go through the process of monitoring, analysis, and profiling and analysis and tuning, right? That's the whole process. We're going to do that every time. So we need the right tools. So let's start with know what we are stressing. Remember this, the speed up targets that the JDK enhancement proposal had? So these changes are already made. So we know that we're trying to stress or find out if changes show up as we see as an improvement or not, right? So first, these are our stresses. So we want to have a test that stresses all these things, okay? So for that, I need to get a workload, right? So of course, because we're talking about contention, you have to look at Doug Lee, right? And Doug Lee, when they were doing for the JSR 166, they were doing testing different optimizations such as reentrant locks and other things. And I just took that benchmark and just looked at the synchronized method in there and picked that up. So for that purpose, I'm going to Doug Lee's expertise and choosing that lock loop benchmark, okay? So this is the main loop that I'm interested in. And you see the keyword here, synchronize this. So basically, I'm just testing this in a loop is what we're trying to do, okay? The second thing is, you know, I got the workload and everything, and I know what I'm stressing, but I have to make sure that I'm in fact stressing what I think I'm stressing, right? So I'm going to stress contended monitors, object monitors. And remember, I was talking about the optimizations in the JVM to avoid you know, going down the slow path. So I'm going to make sure that I, A, bypass bias locking, and then B, do not do stack-based locking. So basically, I want to make sure that I'm using heavy monitors. I want to make sure that when I'm contended, I'm directly going down the slow path, you know, so go down the inflated path, okay? So, and I have, you know, and then this happens to everybody. It happened to me when I tried to do this test for the first time. You know, I was comparing Java 8 and Java 9, and I was like, why isn't this showing the improvements that I think it should show? And that was because bias locking was enabled. So if you go down the stack, which is called the fast path, bias locking is tried first. So they try to bias the lock, and then they unbias it, and it goes there's a lot of, there's bias revocation, and it goes on a different path. So, but I wanted to stress just the inflation and see the difference right there. It was a bit of a problem because I couldn't see that, and I went down a different path. The point being that you know what you're stressing, you have the right benchmark, but make sure that you're stressing the right thing too, okay? What about tools? And I was talking about this particular tool that I've used for a long time, right? It's called Oracle Dev Studio. Okay. It used to be called, if people are used to doing performance analysis, it used to be called Solaris Studio Analyzer, SSA. And if now you download it, you'll still find the SSA acronym in there sometimes. The version I'm using right here is 12.6, which also includes flame graphs. So if people have seen Brendan Gregg's flame graph talk, this particular tool also includes that now. So it's pretty cool. So you don't have to do all the patching and other changes in your code to get the flame graphs. It includes that already. So if I get a chance, I think I should, I'll show you that as well. In its simplest form, the tool has two components. Remember I was talking about profiling and analyzing. So this tool does both. So in order to profile, you can, right now, you can by default, it understands that if it's a Java application, it'll do -j-on by default. So you don't have to specify -j-on, and then for profiling, which we're going to do simple clock-based profiling. There are different ways you can do profiling. If you are coming from hardware background, you may know about performance counters. And performance counters are something that give you a visual inside your hardware, like caches, like hardware level caches, L1, L2, L3. If there are any misses, if there are any translation look-aside buffer misses, and other misses like that, or load and store if you're going to the main memory. So those are called performance counters, and you can profile based on that. And eventually it'll be called hardware counter profiling. But we're not going to go into that. It's a very useful tool to do those things if you do want to look at your cache misses and other things, or memory bandwidth issues or anything. But right now we're just going to dive into the default, which is clock-based profiling. And then you can specify how long you want to record it. You could also specify, like I said, hardware counters. Okay, so that's there. So let's try to look at one of these. So we'll start with the Java monitor enter operation. And I'll quickly show a demo. And if we have time, I'll show you a demo of other tools that I have found interesting over time. So here I have the experiment already open, but let's go start from the beginning right here. So when you, so like I said, there's two ways. So there's the collect, which does the profiling, and you enable collect, you prepend it to your command line. I'll show it to you in a minute. And then after your experiment is collected, you can open your experiment as such. So what you see here is your welcome screen, and you could actually start it from here, from the GUI itself. You could start profiling your application from here. But since I've already profiled my application, I'm going to go ahead and open my experiment. You would open the experiment, you would go through the details of the experiment, and you will try to figure out different components. The other thing you can do, and because I want to compare Java 8 and Java 9, I'll use the compare experiments option, okay? So that's what I did over here with my compare experiments option right there. You could go into overview, and you can see the experiments I'm comparing. The first one I'm comparing is a Java 9 build 133, and I made sure that BIOS locking was disabled and heavy monitors were enabled, and my lock loops benchmark with the number of threads and number of loop the time iterations and stuff like that. The next one, which is called, I think it's called experiment 1, would be my JDK8 build 102. And again, bias locking disabled, heavy monitors enabled in the same parameters to the benchmark, okay? Now let's go to the functions. So by default, it'll show up as user mode. User mode are basically your Java application functions. It'll show all the methods that you had. So as you can see, there's something called static, there's something called JVM system. It doesn't show those things right now because it's just interested, or you are as an application engineer, you're interested in looking at just your application functions. And then these columns. The first one is exclusive, and the next one is called inclusive. So exclusive is, if I'm method A, how much time am I consuming? Just me by myself, none of my colleagues. So method A, if method A calls methods B, C, and D, then all of my colleagues and myself, if how much time are we spending, that would be called inclusive time. So method A by itself and method A, B, C, and D would be inclusive right there, okay? Exclusive, just method A. And then since we see, within exclusive, we see baseline and experiment 1. Baseline is our Java JDK8, no, JDK 9, I'm sorry, and Java 8 is what we are comparing it with, right? But I want to go into more details because remember, this change is within the JVM. So basically, it's within the runtime, right? I want to look at the locks. I want to see what my runtime does with respect to it. So for that, I will choose the machine mode. There are 3 different modes, actually. There's also the expert mode, which kind of combines both of them. But I'm interested in the machine mode. So I'll go here. There are other cool tricks you could do, not tricks really, but you could do like percentage time spent also. So we can do that. So anyway, so let's go and look at other options here. So remember I spoke about the flame graph. We could look at it quickly. It's not going to be that, oh, sorry, it's not available when you're comparing experiments. I thought so. So anyway, so let's go back to caller callies. So what does this mean? So again, when we are talking about lock loops, built-in loops as one of the methods, who is calling lock loops? Well, those callers will be on top. Then you have your main method of interest. And then you have anything that so basically, like I said, method A is calling methods B and C. So, and then those two are calling method A. So callers and callies. So that's what it shows. And for us, it's showing something very interesting. Since we're comparing 2 experiments, you see 0, 0 for those because there's something in these that JDK8 does not call, or probably they don't exist, right? Because remember, JDK9 had new method that was introduced, right? The quick enter. It's not a part of JDK8, so that's why we see 0, 0. But let's look at monitor locking right here. And then we can add or we can set center. Set center means it by itself. So now that becomes the main, and then you have caller callies with respect to that. And then if you want to add, that would mean, so let's see this, and then we say add. That would mean that we're adding the built-in lock loop and the runtime stub, complete monitor locking. And now we want to look at caller callies with respect to those 2. So those 2 become our main methods of interest, okay? So let me try to see if I can summarize it directly with respect to the slides. Okay. All right. So what I did is I went ahead and summarized all the things that I showed you just in bigger fonts. So remember, like I said, we had method enter and slow enter only in JDK8. And for JDK 9, we had a new thing called quick enter, right? So this was what I was showing you over there, right? It's exactly the same. It's just a screenshot, and it looks, you can see it much better here. So if you look at the 4 callees, you see the second one has 0, 0, right? So that means there were no clock ticks in that one because that method does not exist in Java 8, right? It's a quick enter is only in Java 9. So when we compare the JDK 8 and JDK 9 exclusive times and inclusive times, what we observe that in object monitor enter itself, JDK 8 takes more time. And this is 50 seconds. It's because I'm running it in a loop, okay? It wouldn't take that much time, but because I'm running it in a loop, that's how much time it's taking. So you see the difference between like almost half the amount of time exclusive. So by itself, enter only takes half the amount of time, okay? Of course, like I said, quick enter is not there for JDK 8, so we have no ticks. So the 32 seconds are exclusive to JDK 9. And if you want to look at more what this optimization is about, you can go into the source. There are 2 source files here, synchronizer and shared runtime. Because this is a runtime optimization, you have to look at the runtime. So, but go ahead, feel free. Don't get scared. It's not that difficult, but if you compare Java 8 and Java 9 source side by side for these files, then it may be better to understand the changes, right? Because you're just looking at the change set. Java 9 does go to the slow enter path because sometimes it may not find enough optimizations because there's a couple of optimizations that can still be done. So it does do slow enter, but only for half the amount of time, which is pretty cool, right? And then Unpark, I went ahead and did the Unpark thing too, and the Unpark is optimized too. And I'm not able to go into details of that, but exit monitor also. We have object exit and exit epilogue as a part of it. So when you look at the callee stack, you will see that exit and exit epilogue are the part of the stack. And of course, both of them have been improved in Java 9, okay? If you want to read further, there are these things, a couple of things on synchronization, a couple of things on bias locking. If you want to read about Java performance, there's a book by Charlie Hunt and Binu John. You can also look at these mailing lists over here if you have questions on hotspot development itself or garbage collection development. What I want to do is take up the remaining time to show you some of the tools. And I also have a book, I should say that. I have a chapter in a book called, I don't know the real name of the book right now because we're still deciding on the name of the book, but it's a book on Java 9, and there's a chapter on performance optimizations in Java 9, and then I covered this in detail in that book as well. But I want to show you the different tools that I use, okay? So first of all, in the simplest form, and this is just to track simple things, like for example, if you have a smaller optimization and you want to look at how the allocations are happening, right? Memory profiling or whatever. You could use Visual VM, of course, also. But NetBeans has a profiler inbuilt as well, okay? And here in this particular thing, I have a simple. It's just calling these things over here. What I'm trying to show here is this optimization. I was talking about string density. What it does in Java 9 is that the backing array for string has changed from char array to byte array. So what I'm showing here is that I'm running the same benchmark, which does this, creates a bunch of strings, and you can see the backing array is a byte array right there. So the top grocer is a byte array, right? So if I showed you the other one, which is not here, so Java 8, JDK 8 would show you char array. So now instead of having 2 bytes, you have just single bytes, a single byte array. So that's an improvement. So basically your footprint has been reduced to half, right? So that's another optimization in Java 9. When I was talking about monitoring, let me go back here. When I was talking about monitoring, I mentioned about offline logs and and parsing them. So this is a log that's parsed, and I opened it in GC Histo. You can download GC Histo for free. Actually, the Oracle Dev Studio tool is also free, by the way. And what you can do is you can look at how nicely it shows you. This is a parallel GC log. So you can see a bunch of young collections and a bunch of old collections, right? So that's what GC Histo does. It gives you a histogram of your GC pauses, garbage collection pauses, okay? So those are good tools. You can write your own parsers. You can use JFree charts. If you come for my talk tomorrow, I'll show you JFree chart as well, which shows you can plot how your memory occupancy changes over time of your application. The other tool, which I really, really like, and I recently found out about it, which helped me debug megamorphic call site, nested megamorphic call site, is this particular tool. Is called JITwatch. JITwatch, actually, let me go here quickly. And this is not the example, and that was for a client. But in its simplest form, you open a log based on, you have to provide a command line option called print compilation, and then you log it to a file. And it's in the README. If you download JITwatch from GitHub, it's in the README how to obtain this information. So you open your log and you start its processing. It does a bunch of things that are like a recommendation for your code, and then it shows you compiled and uncompiled classes. So all the classes with tick marks are compiled. So for example, I could go, there you go, right? So then it's only showing you tick marks, right? But let's just go look at one of them. And so you could go here, and then you can say non-JIT compiled, but let's just go to this one here. What's interesting to me, I mean, you can look at all these things, but what I wanted to show you here is the try view right there. So right here, so you can see that. So with I think Java 7 or JDK 7 update 40 or maybe JDK 8, tiered compilation was enabled by default. Right? What that means is that your method can be compiled at different levels. Eventually, it goes to a higher optimized level, and you could see those over here. So what you see here is like C1 compiler, because there's a client compiler and a server compiler, and tiered compilation starts as client compiler, eventually goes to server compiler. But here it was at C1 level 3, so it didn't really go to the server compiler. But these things are good to know, and then you can probably even so it shows you the chain here. What it should show you is the well, and this is what helped me look at the nested megamorphic call site, because you could tell it showed me different levels of compilation, and it showed me why. So first it would try to inline something, but that something got recompiled. So of course it has to de-optimize everything and then go back to compiling again. So it went into from compilation to de-optimization to compilation to like multiple times. And I was kind of confused, like why is it doing multiple times? And because of this kind of flow chart, I could understand, okay, I understand now, because the nested side itself is megamorphic. So I'm getting like megamorphic to megamorphic to megamorphic, and it's kind of recompiling and re-optimizing everything else. So very good tool, JITwatch. Let's see what else I have here. Well, I think that's all I have right now. And if you have questions, you can always ask me now, later, email me, whatever whichever is your favorite source. And I'm open to questions now. Said? Thanks.